Please, formal and serious.
Yes.
Because Rosa is the real boss. Eh?
She's the coordinator.
Yes. So, okay. So today I'm super happy to introduce Maria Petropolo. Maria studied and obtained a PhD at the National and Kapodistrian University of Athens in Greece. And then she was awarded the very prestigious Einstein postdoctoral fellowship that she spent at Purdue University. And then she moved as a Lyman Spitzer Fellow to Princeton, which is where I met her. Now she's back home as, very rightly deserved assistant professor in astrophysics at the National and Kapodistrian University again. And incidentally, she has also been awarded a L'Oréal UNESCO Award for Women in Science, and she's a Mercator Fellow. She works on quite many subjects. She has many papers, more than 30 as a first author. In particular, she focuses on non-thermal emission from astrophysical outflows and jets, such as jets. For example, she modeled instabilities and radiative processes in plasmas with relativistic particles, protons, electrons. She's done studies on magnetic reconnection with particles in cell simulations to explain, for example, the powering, for example, of lasers. And she also calculated emissions of neutrinos, making predictions for ice cube, or exploring various kinds of sources, supernovae, gamma ray bursts, blazars again. And she pays attention to observation, which is also great. So she has also worked on X-ray echoes from X-ray scattering of dust particles and did numerical hydrodynamical simulations of winds interacting with disks and pulsars. Today she has the perfect talk for this group. So she will talk about,
Let's see.
Believe me. So she talks about hadronic models for high energy emission from extragalactic jets. So Maria?
Yes, thank you very much for this very extensive and very nice introduction. So let me share my screen. Okay, so can you see now my slides?
Yes.
Yeah.
Okay, perfect. Yes, and as I said before, ideally I wished I would be there, but now I will give you a virtual talk, and at some point I hope to visit one of the universities and institutes in Mexico. So as Yuri said, today I will be talking about hadronic models of high energy radiation from jets. And many of the results that I will be presenting today have been obtained in collaboration with the people listed here. And during my talk, I will say a couple of words about the work of some talented students that I had the chance to work with during the last 2 years, more or less. So with that, let me start. In this talk, I will be focusing on relativistic jets, which are basically collimate outflows of plasma that move with bulk velocities that approach the speed of light. And relativistic jets, as you may know, are ubiquitous in the universe. So they can emerge from the centers of active galaxies that they host accreting supermassive black holes, or from the smaller scale analogs that we know of, which are stellar mass black hole binaries or binaries that host an accreting neutron star. Jets can also be launched during catastrophic or explosive events, such as the collapse of very massive stars, or the merger of compact objects, and these events are well known. These are the gamma ray bursts. They release tremendous amount of electromagnetic energy, and they are perhaps the brightest and more powerful transients in the sky, extragalactic sky. So jets can also be launched during the disruption of a star by a supermassive black hole, which these events are known as tidal disruption events. And as you can see in this table, the jets may have different Lorentz factors, different bulk velocities, and they may release different amounts of power. But despite the differences in the physical conditions of these jets, what they have in common is that they are known to produce broadband electromagnetic radiation. So, and this knowledge has been made possible has been obtained thanks to targeted observations and monitoring of jets, both extragalactic and galactic, with a suite of telescopes and ground-based experiments, some of them that you can see here. Of course, I didn't have space to include them all, so you may not see your favorite experiment or satellite over there. Apologies for that. But just to give you an idea of the photon distributions that we can obtain using the multi-wavelength data from these observatories, I show you four examples. On the top left, we see the photon spectrum from a black hole, from the prototype black hole X-ray binary of our galaxy, which is Cygnus X1. And for comparison, you can see on the bottom left the photon energy distribution of an active galaxy that has a jet 3C273. And you can see that the emission extends from radio wavelengths up to TeV gamma rays. On the top right, as an example, we can see the photon energy distribution of the first jetted TDE that has been discovered in 2011. And on the bottom right, we see now the temporal evolution of the photon spectrum from a very bright GRB that has been detected also in GeV gamma rays with Fermi-LAT. So the fact that the jets are high energy non-thermal emitters basically tells us that they contain relativistic particles which have extended energy distributions such as power loss. And in fact, almost all acceleration processes that you can think of, like shock acceleration or shear acceleration, magnetic reconnection, basically produce power loss that are connected to a thermal-like distribution, which is basically the pool for the high energy particles. And this is schematically shown on the left, where you can see the particle distribution that has a Maxwellian plus a power law. And on the right, you can see how the synchrotron spectra of these particles would look like. And in fact, most observations of jets are consistent with a dominant power law component for the particle distribution, which is here indicated by the dashed line. So now that we have established the fact that there are relativistic particles in jets with extended distributions in energy, let's summarize what are the basic radiative processes that are most relevant for computing the radiation we observe from the jet. So I had divided these radiative processes in two categories, depending on the species of the charged particle that interacts. So let's start with the leptonic ones, which we are mostly familiar with. So if you have charged particles like electrons moving in a region of magnetic field, they're going to radiate synchrotron emission. And then if they interact with low energy photons, they can upscatter them to very high energies, e.g. in gamma rays, via inverse Compton scattering processes. Also, the energetic photons can interact with low energy photons and produce electron-positron pairs. And this photon-photon pair production process is very important for loading the jet with relativistic pairs. Now, if we move to the hadronic processes, again, protons can produce their own radiations via synchrotron emission, but the most important and interesting for multi-messenger applications are the interactions that photons undergo with photons. So protons can inelastically collide with low energy photons, and they can either produce a pair of electrons and positrons via the Bethe-Heitler pair production process, or they can produce pions. And pions are unstable particles, so they will decay into muons, the charged ones, and the muons will decay into electrons and positrons and neutrinos. So photomeson or photopion production is one of the two basically astrophysical processes that they can lead to the production of high energy neutrinos. So if we want to compute now the radiation from the jet, what we need to specify are the emissivities and the absorption coefficients for these processes, and some extra ones if we want. We need also to specify what is the geometry of the emitting region. Is it a slab along the jet? Is it like a spherical shell? Is it a blob? And then solve the radiative transfer equations within that region, and then perform Lorentz transformations in order to move from the co-moving frame of the relativistic jet to the observer's frame. So the Doppler boosting is really important in these calculations. So this was in a nutshell what we really have to know before we start computing things. So let us now have a closer look at the hadronic models of AGN with jets, and I will start with some phenomenology that will be very useful for our discussion later on. So today I will be talking about blazars, and blazars are nothing else but AGN with jets that are viewed at small angles. So we are basically seeing what the emission that is being produced within the jet. And as you can see, the spectral energy distribution of a blazar on the left has a very characteristic shape. It has two components, one peaking at low energies and one peaking usually in the MeV to GeV energy range. And blazars and AGN jets, even though they are persistent sources of radiation, they also exhibit flux variations in time. And this you can see by the different markers here on the plot. These variations in time are known as flares, and I'm going to talk about that later. So AGN jets not only produce gamma rays, but now we know, thanks to the Fermi-Lat telescope, that is an all-sky monitor basically in the GeV band, that they are basically the most abundant population of point sources detected in GeV gamma rays. And they can also fully account for the extragalactic gamma ray background light above 100 GeV or so. Now, blazars can be divided phenomenologically into two major classes, the so-called flat spectrum radio quasars and BLX, depending on the presence of broad emission lines on the optical spectrum. So FSRQs have broad emission lines, but BLX basically have featureless optical spectrum. But behind this observationally driven classification, there are important differences also in the physical conditions of the AGN environment. For example, flat spectrum radio quasars are believed to have a radiatively efficient accretion disk that basically illuminates the gas clouds in the broadline region, and these form an external UV photon field. But on the other hand, BLX are thought to be powered by radiatively inefficient accretion disks, and therefore they do not have any strong external photon fields present. Also, they are thought to have weaker jets compared to the flat spectrum radio quasars. And clearly having knowledge of the radiation fields that are available in the vicinity of the jet is really important when we want to make detailed calculations. So going back now several decades, one of the main questions that arose with the detection of the first blazar jets in gamma rays in the 90s was whether these gamma rays have a leptonic or a hadronic origin. So here I show you some of the very first attempts to model the blazar SEDs. On the top left, you can see, for example, a spectral energy distribution of a flat spectrum radio quasar that was modeled using an external Compton model. In this case, the gamma rays are being produced by Compton scattering the available BLR photons that are external to the jet. Now, if we want to model a BLX source, like the one shown on the top left, we can use a synchrotron self-Compton model. In this case, the gamma rays are the result of inverse Compton scattering of the synchrotron photons that are being produced in the jet. And this is because in BLX, as we said, there are not strong external photon fields available. And despite the sparse data at the time, the first hadronic models for high-energy jet emission also appeared in the early 90s, an example you see on the bottom right. So here, the gamma rays are explained by cascade emission. And what I mean by cascade is the emission that the secondary pairs produced in the jet through proton-photon interactions emit. So here, also the cascade emission, the electromagnetic cascade emission, has a comparable flux to the neutrino flux, which is not illustrated in this plot. But because of this connection between gamma ray fluxes and neutrino fluxes, people tried to basically predict what would be the diffuse neutrino flux from the whole population of blazars, even well before the construction of the neutrino telescopes like AMANDA or IceCube. And this is one of the very first calculations performed by Mannheim in 1995, where you can see with magenta the prediction of the cascade model for radio loud AGN. Now, moving again several decades ahead in time. So after the discovery of the neutrino, of the first high energy neutrinos by IceCube in 2013, the searches for the electromagnetic counterparts of these individual neutrinos became more popular and more interesting. Now, several cross-correlation studies of high-energy neutrino events with catalogs of gamma-ray sources, including blazars, were performed. And what these cross-correlation studies found is that there is an interesting association between neutrino events and BLX sources. And even though the results they didn't provide strong evidence for a connection, they revived at least the interest in hadronic models of AGN jets. Because since the 90s and until the 2010, let's say, people have basically discarded hadronic models and focused on leptonic models for gamma-ray blazars simply because they worked. So why one should bother with more complex models? And the answer here is neutrinos, of course. So motivated by these early results, we wanted to check if hadronic models of these candidate neutrino sources can explain the observations, the neutrino observations. Here I just show you one example from a paper that we wrote in 2015, where we modeled two blazars with leptohadronic models. And what we found by self-consistently modeling these sources is that not in all cases the gamma rays can be explained by the cascade emission. So on the left, you see an example, for instance, where the gamma rays are basically coming from the cascade emission of secondaries, and the neutrino flux is comparable to the gamma ray flux, as I said before. But on the right, you see another example where the gamma ray flux is mostly produced by synchrotron self-Compton emission, and the hadronic component carries only about 10% of the gamma ray flux. So the hadronic fraction of the gamma ray flux can also be modeled or studied through this Y parameter that I show you here, which I define it as the ratio of the neutrino luminosity to the gamma ray luminosity. And keep this in mind because I'm going to refer to this Y parameter quite a lot in the talk. Large Y parameters close to 1 mean that the gamma rays have a hadronic origin, but low values of Y mean that gamma rays have predominantly a leptonic origin. So now, based on this hadronic model that I presented to you for individual blazars, we can move ahead and we can compute the prediction for the diffuse neutrino flux now coming from the whole population of blazars. And here, assuming that all BLX sources have the same Y parameter, which ranges between 0.3 and 0.8, we predicted this range of neutrino fluxes that you can see on the left. So what is interesting here is that even though blazars can account for almost 100% for the extragalactic gamma ray background above 100 GeV, as you can see here, they only can explain about 10% of the total diffuse neutrino flux. And this is because the spectrum is peaking at very high energies, well above the energy range probed by IceCube here, that you can see with the red points. But since then, this was back in the 2016, IceCube has placed some very strong constraints on the model predictions, and these are shown on the right. For example, the extremely high energy upper limits, which are shown with a black line, now constrain this Y parameter of our model to about 10%. So this means that if we take a typical BLAC from the population, no more than 10% of the observed gamma ray flux of that source comes from hadronic interactions. Any questions till here? Okay, I'm continuing.
No.
No.
Yes. No.
Okay, so besides this relation between the gamma rays and the neutrino fluxes that you expect in cascade models for gamma ray blazars, there is another prediction that is the presence of a broad electromagnetic component peaking in the hard X-rays and in the MEV band, as shown here by the shaded region. So this component again arises from synchrotron radiation of secondary electrons and positrons that are predominantly produced via the Bethe-Heitler pair production that I mentioned at the beginning of the talk. So one can show even with back of the envelope calculations that the predicted neutrino luminosity is of the same order of magnitude as the luminosity produced by these pairs, by this process. So if we have available in the future a sensitive all-sky monitor in the MEV band, like Amigo X, for example, is really important for searching for these types of signatures, because right now we don't have a sensitive all-sky monitor in the MEV, and we are actually pushing for that as a community. And also, if we have broadband sensitive hard X-ray monitors, like HEAP, which is going to be the better version, a bigger and better version of NuSTAR, this again will really help searches, the multi-message searches of blazars in the future. But besides this cascade model that I described to you so far, there are other variants of hadronic models for the jet emission from HEN. An example is the so-called proton synchrotron model that has been proposed by a Hadronian in 2000, I think. And according to this model, the gamma rays that we observe from the jet are basically the result of synchrotron radiation from ultra-high energy protons. So, as you may think, the neutrino predictions of the proton synchrotron model are going to be very different compared to those from the cascade models. And this is because the proton synchrotron model requires different physical conditions in the source, like the magnetic field strength is different, the photon densities are different, as well as the maximal proton energies are different between these two models. So here on the left, you can see an example of a proton synchrotron model applied to a BLAC, the Blazar Markarian 421 that you may know of. And the predicted neutrino flux is shown in blue. And you can clearly see the difference compared to the previous models. So the neutrino fluxes peak at EeV energies now, not PeV, and also the neutrino flux is much lower than the gamma ray flux. So this Y parameter is much less than unity in these cases. Because of the shape and flux of the neutrino spectrum in these models, the current instruments like IceCube and Antares are not very sensitive to these model predictions. But however, in the future, if we have a large radio neutrino telescope like GRANT, which is a proposed experiment to be built in China, I think, they are going to be really sensitive in these very high energy neutrinos, and probably we are going to be able to test this model for blazars in the 2030s, hopefully. But so far I have been talking about modeling the blazar spectra that were constructed using observations that were averaged over a long period of time. So I have neglected any information coming from the temporal variability of the source. And as I told you before, and as you can see here in this animation, the emission from the jet is variable, and it can vary on different time scales and with different amplitudes across the electromagnetic spectrum. But why is it important for the discussion of neutrino production from jets? Why is it important to consider this variability in the blazar flares? One answer to this question is the following. If we consider that a flare happens at low energies, for example, in the optical or in the infrared wavelengths, then you can imagine that during a flare, the number density of photons in that energy range goes up. So if the number density of photons goes up, this means that the optical depth for photon-proton interactions also goes up, as indicated by the equation in the bottom. So during flares, we expect the neutrino luminosity to go up because the opacity goes up. Similarly, if we consider a cascade model where the gamma ray flux is proportional to the luminosity of the cascade, if the gamma ray flux goes up, then the cascade luminosity goes up and the neutrino luminosity goes up as well. And from an experimental point of view, during flares, the expected contribution from the atmospheric background in neutrinos is going to be smaller, so it's going to be easier to detect significant neutrinos, let's say, during flares, during shorter time periods. So based on this discussion, it comes as no surprise that the first astrophysical neutrino source that has been significantly associated both in time and space with a high energy neutrino was indeed a blazar that you know of by now, Texas 0506 plus 056, that was undergoing a major gamma ray flare. On the left, you can see the unique multi-wavelength data set that we obtained in 2017. And different groups tried to model independently this data set in order to see whether or not we can explain the detection of that neutrino event. So what did we learn from the detailed analysis of this data set? First of all, we excluded cascade models for the Texas source. So the gamma rays would not be coming from a cascade of secondary particles, but they are basically explained by the inverse Compton scattering of low energy photons by electrons in the jet, accelerated in the jet. And this is in contrast to the earlier results that I showed you before, a couple of slides before. So any hadronic related emission in the Texas source, we showed that it should be subdominant, as you can see here by the blue line. So the hadronic component should be below the X-ray flux. And actually, one can show with back of the envelope calculations again that the maximal neutrino flux we expect from this source is basically set by the X-ray flux of the source, which means also that when we are looking for multi-messenger, when we are looking for neutrino counterparts to blazars or other jets, it is also important to keep in mind that the gamma rays are not always the best probe for that. X-rays might also be very important. But since the detection of this high-energy neutrino event 1709-22A from the Texas source, a few other interesting associations of blazars with neutrino alerts have been reported. And here I have a very detailed slide with information about these associations for someone who is interested to have a look at later. But what I would like you to take away from this slide is that all of these sources, all of these blazars are very different to each other. So they have different intrinsic gamma ray luminosities, as you can see here in the plot. They have also different spectral classes. One of them is a flat spectrum radio quasar, the one here with the cross. One is a very weak gamma ray source, a BLAC, and the one is Texas and another source that is similar to Texas, which is a masquerading BLAC. So all of them are different. Can we learn something by modeling these different sources in gamma ray luminosity and spectral shape? And I think the answer is yes. So under the hypothesis that these associations were real, we can apply leptohadronic models to the blazar SEDs, and we can see whether or not the neutrino predictions are comparable to the neutrino fluxes inferred by the detection of these neutrino events. So you can see the results on the top left, where I show you the models that are the most promising in explaining the neutrino emission from these sources, and the neutrino predictions on the right. It is also important to note that in these models, the parameters that describe basically the population of the relativistic protons in the jet, like the power loss slope, the maximal energy, and so on, are usually unconstrained. So what we are doing is that we are choosing them in a way that maximizes the neutrino emission without actually distorting the spectral energy distribution of photons. But What we can do also now is that because we are modeling blazars with different gamma ray luminosities, we can basically check how this ratio, this Y parameter, changes with luminosity. And what we see is there is an interesting trend. We see that as the gamma ray luminosity of the source increases, the Y ratio decreases, meaning that the leptonic contribution to the gamma rays becomes more higher, larger. Is there something behind this trend? Is this trend physical or not? Is it a result of the modeling? It's unclear yet. Moreover, what I would like you to look at is that these models require very high baryonic loadings. So the proton luminosity is orders of magnitude higher than the observed gamma ray luminosity. And also the jet power, the inferred jet power, is orders of magnitude larger than the Eddington luminosity of the supermassive black hole. So the question that arises now is whether or not we can actually interpret these findings in a common framework, and if there are ways to basically decrease the energetic requirements for these models and the baryonic loading. And in order to address this question, we worked out with my former master student Philippos a simple but I think physically motivated multi-messenger emission model for jets. And the main idea here is that there is a conserved quantity according to ideal MHD jet theory. And this quantity is called mu here, is the total jet energy flux per unit rest mass energy flux. Now one can show that this conserved quantity is equal to the product of the bulk Lorentz factor of the jet and this quantity 1 plus sigma, where sigma is the plasma magnetization. So this means that if all jets had the same mu parameter, then faster jets would have lower magnetization and vice versa. So what we try to do in this model is basically to connect all the main model parameters like the magnetic field strength, the particle injection luminosity, the slope of the particle distribution, the jet power, the broad line region luminosity to some main parameters. And the main parameters of the problem, as you can imagine, is the jet bulk Lorentz factor, is the magnetization sigma, and the dimensionless mass accretion rate onto the black hole. So I'm not going to go into the details and describe these equations, but that's the idea. We have three main parameters, and we want to connect all the other model parameters to them. And this is what we get. So if we consider a given mu value and we simply change the magnetization, we can generate a family of spectral energy distributions that you can see here on the left that basically resemble different classes of blazars. With dashed lines here, I show you the predicted neutrino flux for each blazar that we simulated. And there are some interesting findings here. So first of all, we find that low luminosity blazars, like the red and the purple one here, resemble the BLX sources. And these blazars in our calculations have weaker jets, they have higher magnetization, harder particle distributions, and they produce neutrinos with a luminosity which is comparable to the gamma ray luminosity. On the other hand, if we look at the high power, high luminosity sources, which resemble the flat spectrum radio quasars, what we obtain is that these simulated blazars have powerful jets, they have lower magnetization, they have very steep power law spectra for the particles, and they are very dim neutrino sources. So here in this framework, we are able to basically construct physically, let's say, this trend that I discussed before. This Y parameter decreases with increasing luminosity, as we can see here. And also the required baryonic loading in this model is not extreme, it's of the order of 10. The jet luminosity, on the other hand, is also considerably lower than before. So I think this is a promising framework for computing the jet emission model in a more constrained way. And as a future step, it would be interesting basically to check the consistency of this model with the diffuse neutrino flux measurements. So to check the predictions of to check the predictions of the model for the diffuse neutrino flux, and perhaps discuss the connection to the cosmic ray fluxes that I have not discussed so far. So this brings me to the second part of my talk, which will be focusing on the hadronic models for gamma ray bursts. And I think this is a good point for me to stop and ask if there are questions.
Enrique, please.
Yes, thank you. So you're saying that there's not too much relation between the magnetic field and the amount of hadrons you have in the jet region. Is that correct?
I think
yes. Yes, you mentioned here weak dependence of baryonic loading.
Yes, okay. It is true that we do not find we find almost a constant, let's say, baryonic loading needed, independent of the magnetization in the emitting region.
Okay, so let me try to see if I can understand. So I'm coming from a different region, more to do with the central engine rather than the jet. And you mentioned before that in some of these you may have super Eddington accretion. Is that correct? So where is all this material coming from? So I'm guessing these monsters are 1 million, 10 million, probably 10 billion solar masses. So the accretion rate to beat Eddington there is quite large. Right?
Yes, you're absolutely right. And this is a very weak point of all of these models because there is no physical explanation for that. And to make things even worse, I talked about two different classes of blazars or AGN, the flat spectrum radio quasars and the BLX. And BLX are thought to have a small accretion rate. So let's say 10 to the minus 3 of the Eddington accretion rate. So the question is, if you have such low accretion rate onto the black hole, how can you produce so much powerful jet? And this is a problem for the hadronic models that I was describing so far.
Right.
One potential avenue was like these magnetically arrested disks that they launch jets, and they have been shown by simulations to produce powerful jets that they have, let's say, a power which is 1.5 up to 2 times the accretion power onto the source. But in order to have this, you need to have very strong colloidal, very strong large-scale magnetic fields threading the disk. You need to have thick accretion disks as well. So to my mind, it's again an open question whether or not you can explain such powerful. Definitely you cannot explain jets with power like 100 times of the accretion power. That's out of the question physically so far.
Right.
Yes.
So here you have very rather low gamma factors, right? So there's not too much beaming.
There is beaming. The gamma factors here are of the order of 20.
Right. So they're not too large. So what do you think then would be the central engine using? Would it be a Blanford-Snijek or a Blanford Payne? So where is this jet being produced?
That's a very good question. That's a very good question because I think that it makes sense to have a Blanford-Snijek process operating as long as we have some large-scale magnetic field again close to in the inner parts of the accretion disk.
Right, but you discard that one, right? Or I think
yes.
You mentioned that you don't seem to have a very large magnetic field, so.
I don't think I mentioned a very large magnetic field.
I probably phrased it wrong. I think you mentioned that there's a small magnetic field. So then that wouldn't help much with the Blandford-Snijek model as
Yes,
the main input.
So there is also another point that the magnetic fields that I'm talking about refer to distances well beyond the center. At distances far away from the central engine. So it could be possible that the magnetic field close to the black hole or to the base of the jet is thousands Gauss, but in the emitting region is much less than that. It's 1 Gauss, for example.
So if you had Blandford-Snijek or Blandford-Payne, would that change the hadronic or the leptonic model in one way or another? So would it favor one of them?
You are asking very good questions. So the thing is that if you have a purely Blandford-Snijek process, this will generate most likely an electron-positron jet. So it's very difficult to explain again how you're going to load the jet with protons. Mm-hmm. So then comes the Blandford-Payne or the wind from the disk. So it is possible that you have both processes operating. And I think this is a more consistent picture. You have the inner part of the jet, the core of the jet being produced, in my opinion, by the Blandford-Snijek process is dominated by electrons and positrons. Mm-hmm. But then you also have another component, which might be a fast wind, for example, from the accretion disk that is also baryon loaded. And the interface of these two is where the action happens, I think.
And would that be able to so if that were the case, would you still be able to focus it with the gamma factors that you have? Or I'm thinking a little bit in all these GRB lingo, and there's these top hat jets versus these I forget the name right now, but probably Fabio or one of them remembers. Structured jets, that's the word. Mm-hmm. So this scenario that you are mentioning right now would give you the chance to have a structured jet, but I don't know if it would then be focused enough for you to detect it. Uh-huh.
So definitely one could work out a structured jet, and there have been some models discussing a two-component jet, so a fast core and a slower sheath, this by Ghisellini and Tavecchio. But ideally, one could be able to construct a structured jet model. This has not been done yet, as far as I know, in radiative models for blazars. So what I have been describing so far and what is being done in the field till now is that we consider one single region and we compute the radiation from it under given assumptions. Ideally, we would like to have computation of the radiation, let's say along the polar angle of the jet, capturing different conditions, but this has not been done. So I cannot answer yet what would be the outcome.
Right, but okay, so let me just think about a little bit what you said, and probably at the end I'll ask a bit more on this. Thank you.
Thank you. Yes. Okay, so I will now step to the second part, which will be focusing on hadronic models for gamma ray bursts, and definitely this is not a complete review. I'm going just to touch upon a few things that I found interesting. So probably I don't have to introduce GRBs in the audience, but just for completeness, just to say or remind that GRBs, as their name suggests actually, are gamma ray flashes that can last from a fraction of a second up to tens or even hundreds of seconds, and they release tremendous amount of energy in gamma rays. ranging between 10 to the 51 or even beyond 10 to the 54 now ergs. Now, the light curves of these bursts are very different, as you may see in the bottom left, but they typically consist of many pulses, and on top of these pulses, one can actually detect short time variability. Interestingly, despite these differences in the light curves, the photon spectra are quite similar. So they are broadband, they peak close to somewhere around 0.1 MeV or even up to 1 MeV, and they can be phenomenologically described by a smooth broken power law, which has been known as the band model. And almost 50 years after the discovery of gamma ray bursts and thousands of hours of observations, the physical origin of the prompt emission is still an open question, is still being debated. And as you may imagine, the first model that has been proposed and has been around for several decades now is the synchrotron emission of electrons accelerated at internal shocks that they occur within an inhomogeneous outflow launched from the central engine. And here is an example of the synchrotron spectra that you expect from electrons that cool. Just to mention what is the idea of cooling, fast cooling electrons that you can see here on the bottom left are basically electrons that cool down to the rest mass energy, basically within a dynamical time scale. So the whole distribution of particles cools down to gamma of 1, can cool down to gamma of 1. Now, slow cooling particles that you can see on the top, they can cool up to a Lorentz factor, which is still much larger than unity. And there is an intermediate case, which is called marginally fast cooling. So the idea here is, depending on the degree of cooling of the electron population, the spectra, the synchrotron spectra are going to look different. And this is illustrated on the right. So, for example, in the fast cooling scenario, the photon spectrum below the peak is a power law that has a photon index of minus 1.5. And this has been in tension with the values or the photon indices inferred from modeling GRB spectra using the band model. However, recently, Burgess et al. In 2020, they applied a physical model, which is time-dependent electron synchrotron model, to a sample of GBM-detected bursts that had a single peak light curve, and they forward folded the model spectra to the detector and then performed the fits. And the results of the fits can be shown on the right. So here you can see the posterior distributions from the modeling of these sources. And the x-axis, you can see what is the photon index below the peak, the alpha parameter. And interestingly, the results could be fitted with this model. And as you can see, some GRBs were requiring fast cooling electrons, others were better explained by slow cooling electrons, and so on. So what is interesting here is, first of all, the electron synchrotron model, at least for this sample of bursts, seem to work. And then that there are different conditions in different GRBs that, for example, like the magnetic field strength might be different in different GRBs in order to produce fast cooling or slow cooling electrons. But this is not the only case, because recently also Oganesyan et al. Studied a sample of GRBs that have been detected in the prompt by Swift, XRT, and BAT, and also in certain cases had available optical prompt observations. And they discovered the following interesting thing: a break somewhere between 1 and 10 keV, so at low energies, which was consistent with a cooling break. So Oganesyan et al. Interpreted this again as a result of electrons cooling down to a Lorentz factor, which is not close to 1, but higher than that. So electrons in the marginally fast cooling regime. However, Ghiseline et al. Also pointed out the following, that if you want to explain this break with incomplete cooling of electrons, then one would demand relatively low magnetic field strengths in the emitting region to avoid the synchrotron fast cooling, and at the same time, relatively large radii in order to avoid the strong SSE cooling. But the question then is, how can we reconcile the observed short time variability detected in GRBs with the large emitting regions? And then Kizellini proposed an alternative. Let's replace the electrons with protons, because we know that protons are not as efficiently cooling as electrons by a synchrotron. So this tension might be lifted. So what we did with Iulia Florou back at the time when she was a PhD candidate at the University of Athens is that we tried to take this sample of bursts observed by Oganessian and test this proton synchrotron scenario. So first of all, we extracted the physical parameters like the magnetic field strength, the minimum proton Lorentz factor, and the proton luminosity that are needed in order to explain the observations. And as you might see from these histograms, the main results are the following: that you need in the source very strong magnetic fields now of the order of mega Gauss, and at the same time, you need relatively low proton energies. So the minimum energy of the proton distribution should be somewhere between 100 TeV and 10 PeV in the observer's frame if we account for a range of bulk Lorentz factors from 100 to 1000. So this means that the Poynting jet luminosity in this model would be very high, like 10 to the 54 ergs per second. So besides computing the necessary, let's say, physical conditions in the emitting region, we wanted to compute also the photon spectra in the proton synchrotron scenario, but taking into account all the relevant physical processes that I mentioned at the beginning. And here you can see the example, the models for two values of the bulk Lorentz factor, gamma 1000 on the left and 300 on the right. And as you may see, the case of gamma equal 300 is already excluded because it overshoots the data in the X-rays. And this is a result of the cascade emission, which is very bright here. And why is that? Because as gamma factor goes down, the density in the emitting region goes up. And as the photon number density goes up, the opacity to photon-photon and photopion production goes up. And this leads to the overshooting of the data. So what we were able to show is that if you want to explain this break in the XRT band with a proton synchrotron scenario, one needs very high Poynting jet luminosities and very high Lorentz factors. So the question is this like, first of all, is this low energy break common to many bursts, or is it a coincidence? And what are the implications of this proton synchrotron scenario for, again, the diffuse neutrino fluxes of GRBs? Because this model predicts neutrinos that are peaking to much lower energies than the typical models for neutrino emission from GRBs. So the neutrinos peak close to somewhere between 10 and 100 TeVs. But so far, I have been talking about the KV and MEV part of the GRB prompt spectrum. What is also interesting is to consider the detection of several bursts at higher energies, above 100 MeV, by the Fermi-LAT satellite. And this has opened a new window. And usually when we talk about LAT-detected GRBs, we have in mind these LAT light curves that are very smooth and have a power law decay in time, which are suggestive of an external shock origin. However, in this big sample of LAT-detected GRBs, there are a couple of them that they show evidence for an internal origin for the LAT emission. And here you can see two examples. So the evidence, first of all, is that the LAT light curve is variable and shows variability patterns similar to those or consistent to those detected in the GBM. And then also the high energy spectrum in the LAT band appears to be a continuation of the high energy part of the GBM spectrum. So it could be possible that a couple of these GRBs have a very bright emission in the GV band during the prompt phase. So 1 year ago, when again Annika Rudolph was a former PhD at DESI in Choeten, we collaborated and we wanted to check, to investigate if this high energy emission in the LAT band during the prompt emission can be explained by hadronic processes, by cascade emission, for example. So for this purpose, Annika considered now a multi-collisional internal shock scenario where collisions occur at different radii and dissipate different amounts of energy. While each collision occurring at different radii, as you can see, it can also probe different physical conditions in the outflow, such as the magnetic field strength will be different, as you can see in these 2D histograms. What we did is that we assumed a fraction of the dissipated energy goes into the acceleration of electrons and protons, and Annika computed numerically the radiation from every collision that you can see here, while accounting for all the leptonic and hadronic radiative processes. So what she was able to do, she was able to compute the spectra from every collision and then sum them up in order to compute the emission from the full burst that you can see as an illustration on the right. And this is a very important step forward to previous multi-messenger studies of GRBs, where typically the photon spectrum is taken to be a band function, and then we compute the neutrino emission using this fixed target photon spectrum. But here we do it everything self-consistently for every collision. And also it's a step forward compared to the standard one-zone models where a single cell, a single internal shock is taken to be the representative for the full burst. But clearly there are several collisions that they contribute more to the observed burst and not a single one. So because I'm talking about, again, multi-messenger emission, one important parameter, as you might have seen, is the baryonic loading. And here I will be showing you what is the impact of the baryonic loading in the GRP jet by looking at the photon spectra. So on the left, you can see the time integrated now full spectrum of a GRB for different choices of the baryonic loading. And as the baryonic loading goes up from 10 to 100, you can clearly see the modification of the photon spectrum. You see that the spectrum is being distorted and enhanced both in the GBM and LAT bands, but also at lower energies in the optical as well. And this result is is basically attributed to the emission of the cascade produced by the secondaries from the secondaries produced in photohadronic interactions. So clearly, if we see distortions in the LAT or very flat spectra in the LAT, could be an indication of a high baryonic loading. Now, what we can also do is compare the neutrino predictions of the model with current stacking limits by IceCube, and this is illustrated on the figure on the right. So in order to be consistent with the stacking limits, one would need a baryonic loading between 3 and 10, assuming now or focusing on very energetic bursts. So assuming that we consider proton acceleration to a subclass of GRBs that have EISO greater than 10 to the 54, for example. And another interesting point is that this baryonic loading of the order of 3 to 10 is also needed, is also consistent with the value that is needed for powering the ultra-high energy cosmic rays with energetic GRBs only, not accounting the typical luminosity GRBs, only using this very small part of the energy distribution of GRBs. And as you might have thought, I couldn't finish this talk without talking about this extraordinary GRB. While we were wrapping up the paper on the topic of energetic GRBs, this 221009 GRB happened. And this was, we could have never wished for a better case study for our model, because this burst is so bright, basically, that caused pileup in many of the GRB detectors, including the GBM, Agile, LAT, and so on. But still, there are some available estimates of the isotropic energy, which tends to be of the order of 3 times 10 to the 54. And this burst had an interesting also light curve, which consists of a few bright pulses at the beginning, and then a quiescent period of about 200 seconds, and then followed by a late time pulse. So what we did with Annika is that we took this basic information about the total isotropic energy in gamma rays and roughly the peak energy of the prompt emission spectrum, which is of the order of 1 MeV. And using the observed light curves, we set up a model that reproduces roughly the structure of the light curves. So the model light curve that you can see here is the magenta, and overlaid on the plot, you can see with light colors, light lines, the observed conus and integral light curves. So what we found when modeling this source is that it is possible to explain the lack of neutrino emission, because IceCube did not detect any neutrino from this very bright and nearby GRB. So you can set an upper limit. Based on this upper limit, we were able to show that it is possible to explain this GRB with a leptohadronic model with a baryonic loading of the order of 3 to 10 and having Lorentz factors of the order of a few hundreds. The isotropic kinetic energy of the jet is of the order of a few times 10 to the 56 ergs, which is consistent if the central engine is a maximally spinning black hole with a mass of the order of 10 solar masses. But scenarios that have even a higher baryonic loadings, like 30, would be in tension with the upper limits and also would require even more extreme isotropic energies for the fireball. So these are, I think, excluded. So this brings me to my conclusions. Relativistic jets are high energy non-thermal emitters and are great particle accelerators. IceCube, thanks to IceCube, the interest in the hadronic models for jet emission, not only from extragalactic jets, but also from galactic jets, has been revived. There are many variants of hadronic models that yield different predictions for neutrinos and source energetics. What we learned the recent years is that the blazar GVT-V emission has likely a leptonic origin, and any hadronic contributions are best probed now with hard X-ray and MEV gamma rays instead. There is an interesting finding of KV energy breaks in prompt GRB spectra that actually challenge the electron-synchrotron cooling scenarios. And maybe this is evidence for proton synchrotron scenarios. And finally, energetic GRBs with isotropic energies exceeding 10 to the 54 ergs per second with moderate baryonic loading of the order of 3 to 10 could be the sources of ultra-high energy cosmic rays and still be consistent with IceCube neutrino limits. And GRB 221009 is an ideal candidate for this type of source. So thank you very much for the attention, and I'm happy to take more questions now.
Thank you, Maria. So let's start with the questions. Enrique, please.
Thank you. Thank you for the talk. So I don't think I follow that 10 to the 56. If I have 10 to the 34 10 to the 34 grams for a 10 solar mass, or 2 times 10 to the 34 for 10 solar masses of energy. So 10 solar masses converted into energy, that gives me 2 times 10 to the 55 ergs, not 10 to the 56. So in order to get 10 to 56, I would need 100 solar masses, and I think the most efficient Penrose processes, you get maybe 10%, for example, for Blanford-Snijek, So you need something like 1,000 solar mass black hole, where 10% of its mass gets converted to give you 10 to the 56. If I didn't mess up somewhere,
So,
right?
Yes, I see the point. I think here what I didn't mention is that this is the isotropic equivalent kinetic energy. So one needs to take into account, if one wants to compute the true energy, one should correct with a beaming factor, assuming that you have a well-collimated jet.
Right. So if you had that, you would get 10 to the 54-ish, right? And that still means 10 to the 54. So that's still one solar mass converted into beamed energy, right?
Right, yes.
Okay, which is still
it's
quite
extreme.
High compared to
it's high,
right?
But not. I don't think that this is excluded, because the beaming correction here is more than a factor of 100. If I remember correctly, they have estimated it's almost 300, the beaming factor correction, because the jet. Because based on preliminary again analysis of the afterglow light curves, they estimate a jet break from the jet break an angle, opening angle of the order of 3.5 degrees for the jet. Which if I remember correctly translates to a beaming factor correction of 250 or 300, something like that.
Right. So you would get 10 to the 54-ish for the energy.
Yes.
And if I remember, but Fabio might correct me here, the largest energies for once you correct for beaming are 10 to 51-ish or 52-ish, Fabio?
Yeah, 10 to the typical energy is 10 to 51. Yeah, like a few times 10 to 51. There are these papers at the beginning of 2001, 2002 by Frey.
Oh,
the thing is, however, I think that even if you don't account for any baryons, so if you consider only electron-positron jet and you compute again the same, and you compute what would be the required isotropic equivalent energy, would be close to 10 to the 56 again, because the baryonic loading here just give you a factor of 3 more in this calculation. The thing is that the isotropic gamma ray energy is so bright here, it's of the order of 3 times 10 to the 54 or even more. So I think we need something which is well beyond the typical GRB, right?
Right.
So, but if you take 3 10 to 54 and 3 degrees, you get 10 to 52, no? The jet energy, so that's more or less the typical one. Right?
Yes, for the gamma rays.
For the gamma rays, yeah.
But okay.
I'm lost here. Why did you put 10 to 56?
So just to say something, that if the gamma ray isotropic energy is of the order of 10 to the 54 ergs, one needs to take into account the dissipation efficiency, which in the internal shock scenario is rather low. So it's of the order, in our simulations, turns out to be 4%. So when we compute the kinetic energy of the outflow, not the radiative energy of the outflow, it's even higher.
I see.
Right, but that would mean that so in order to get 10 to the 56 in kinetic energy, that means you converted something like 100 solar masses into kinetic energy, right?
In true energy would be something like 10 to the 54.
Okay, so, all right. Okay, I'm a bit lost, but okay, all right.
Can I ask something related to this?
Yes,
before Enrique goes to the following.
No, go ahead, Fabio.
So if you have 10 to 54 ergs of energy, what about when the jet decelerates and begins to emit the afterglow emission? So the afterglow emission will be incredibly bright, no?
Right. So that's something that I haven't looked into in particular, and you're absolutely right that if you have a very high kinetic energy in the outflow, then you should see it somewhere in the afterglow. And if you don't see it in the afterglow, if you don't see a very bright afterglow, I don't know what this means. This means either that somehow energy has been dissipated in between and you have not seen it, which I don't think it's physically possible, or that you cannot have such high kinetic power, which means that the internal shocks are not a good candidate for dissipating the energy, which means that you have to rely to magnetically dominated perhaps jets, where you can dissipate the energy more efficiently via reconnection, where you can transform, let's say, almost, let's say, 1/3 of the kinetic energy into radiation and not 1%.
Also, the efficiency by internal shocks can be much larger, no, than 4%. Anna, do you remember the paper we were discussing? Which paper was that, Anna? Are you there?
I think
Oh no, Anna is not here. Sorry. But there was a paper discussing things, I don't know, 2007, 2008, something like that. Claiming that the efficiency can be much larger, no, than 4%. But anyway, I have a question about this. So about the Ghisellini models, no? You say that the rate should be very large. What do you mean by that? So what would be the...
Sorry.
If you have a leptonic emission?
The question is what I mean by large.
Yeah, this one. The emitting region is large.
Yes.
How large?
Yes, so if I remember correctly, because unfortunately I don't have the slide here with that, Ghisellini was claiming that for a typical variability timescale of 1 second, he would need a radius of the order of 10 to the 15 or 10 to the 16 centimeter.
Okay.
Yes, in order to avoid the SSE cooling.
And the problem then is the time scale for the fluctuations.
Yes. Yes.
But in that case, you can assume that you have like a patchy model or something like that, right?
Yes, then you can do this perhaps. But again, yeah, you can have a patchy model, but again, how you need to have big chunks of the jet, big emitting regions still. No?
Yeah, to have enough, To
have enough particles.
If you have a small region, again, you have an efficiency problem, no?
Yes.
Yeah, it's tricky.
But I'm not sure, however, if these bursts that have been studied by Oganessian, what is the typical variability timescale? So, because based on the light curves that I have seen in the paper and an example you can see here, I'm not sure if you can see very short timescale variability, but rather more smooth pulse. So, yeah.
But what about other GRBs?
So the thing is that they don't see these breaks in many GRBs simply because there are not many with coincident XRT and back detections.
Yeah.
So I'm not sure what's the variability timescale or how common the break is in other GBM bursts.
Yeah, so it can be just this case, no? Yeah, or just a few cases, yes.
I mean, they had a sample of, I don't know, perhaps 20 GRBs.
Oh,
yeah,
okay,
but...
Okay, many thanks.
Thank you.
Hi, Maria. Thank you for your presentation. So I
Thank
have a really naive question. So sorry if it's very simple. But
no, please go ahead.
At the end of your talk, you mentioned the study that you are doing with the URB 221009. But what's the
Yes.
difference? I understand that this is the highest energy photon detected ever, or emission detected ever for a GRB. But this could be, or your study could be applied also for to the URB, the other famous is 1901 14C that it was detected with the MAGIC observatory. So how this could be tested in other GRBs?
How this could be tested in other GRBs. So yes, I think for the GRB that you mentioned, the very high energy photons also were detected during the afterglow. So I'm not aware of what happened in the prompt emission, but I think, I think what is missing here, to be honest, in order to test crucially a model for these energetic GRBs, because energetic, I mean those that have isotropic gamma ray energies above 10 to the 54, is basically to have a physical model that connects the prompt to the afterglow. Because as it was mentioned before, if you have very high kinetic energy in the outflow, which might be needed in our model to explain GRB 221009, you should somehow see a very powerful afterglow. And if this is not the case, why? So I think, yeah, but I don't have a very clear answer to your questions, unfortunately, how you can test it. But otherwise, you can, again, test it using multi-messenger emission. So try to see what would be the predictions for neutrino emission and compare to the available upper limits by IceCube. So this can somehow constrain some parameters like the baryonic loading of GRBs, but it does not test in a sense, it cannot tell you, it rules it out.
Okay. Thank you.
Thanks.
Yuri, please.
See, also many thanks for the talks.
Thanks.
It's a bit late and you have received a lot of questions, so super
No,
short.
that's fine.
Super short. Well, it's a sign it was interesting. When you showed the modeling, no, that Annika, if I remember what I didn't understand, it's very basic question. What I didn't understand if the different places, the different conditions come just from a fit or are based on like you have a simulation and you take the conditions along a simulation. That's what I didn't understand.
Yes, you didn't understand because I didn't explain it. So yes, so we don't actually have a hydro simulation, for example, and we track internal collisions in the simulation. So what we do is that in order to reproduce the structure of a light curve, so to have two pulses and some quiescent period and something like that, we need to tweak the distribution of the initial Lorentz factors of plasma cells launched from the central engine. So it's basically the model setup, if you like. We can experiment with different types of distributions. And this is an example where we have relatively a well-behaved central engine emitting plasma cells with not very different bulk Lorentz factors. But I don't remember here the details exactly of how the distribution looked like. Ideally, what you say is the next step to have like a hydro simulation with high enough resolution to be able to identify shocks. And then do on top of that the radiative transfer, or at least use the information from the hydro simulation in these radiative models.
Yeah, kind of a post-processing.
Yes, like something like post-processing.
Because then you can also establish more links, no, between all the other questions that they ask with the observations. But it becomes a huge work, of course. So. Yeah,
this is the direction that we should go slowly as a community. At least for leptonic models, this can be easily done. For leptohadronic models, is more complicated. So yeah, so this is like the state of the art right now for radiative modeling. If we discard protons, I think we can start moving toward coupling the hydro and radiative calculations together.
Okay, thanks. Again, question from an outsider. Huh?
No, perfectly fine.
Okay, thank you very much.
Thanks.
So there are more questions, comments, suggestions? If not, I think that we can thank again Maria because it's very late for her. So thank you so much.
And it's holiday.
Maria.
It's holiday.
It's holiday.
It was a great presentation. So thank you very much for coming and for accepting our invitation.
Thank you very much. And also for the questions. I don't know if I answered all questions, but yes, and feel free to send me an email if you have comments or want to share some papers and stuff like this.
Thank you. Perfect.
Yes.
Great. So
Okay.
see you next week.
Bye-bye.
Thank you, Maria. Bye-bye.
Bye.
Thank you.
Bye.
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 Yeah.